usually talking about conventional composite polymer composites, where we have at least one component. So we have a multi-component dielectric, and we are talking about at least one component which possesses nanostructures. And the importance is that because of the presence of this nanostructure, there is a significant change in the properties of the dielectric. The concept of nanodielectrics was presented by Lewis in 2001. And the idea was this, that polymer nanocomposites, the properties of the polymer nanocomposites could be shaped, dictated, or affected by nanoscale manipulation, that is by incorporating nanofillers. Now, if you look at nanodielectrics, what is really very different? We have been incorporating, yeah?
Please hide this window at the bottom. It is interfering.
Okay, sorry. Yeah.
Thank you.
Right now? It's okay
Yes,
now? Yeah, okay. So if you, what is important, what is so special about nanodielectrics? It's not, I mean, we have been putting fillers into materials from a long time. But the difference is that we see a significant change in the property by incorporation of a very small number of small amount of nanofillers. By incorporating 2%, 3% by volume of fillers, we are able to affect a significant change in the property of the composite as a whole. And this is what is intriguing. Now, if you look, I have on this slide, if you look at this rectangles with the square circles in them, each of these rectangles have the same amount of polymer composite, the bulk polymer, which is represented by the blue region, and a same fraction of nanofiller, which is represented by the pink region. What is changing as we go from the rectangle at the top to the rectangle at the bottom? What is changing is the size is decreasing, the size of each individual particle is decreasing, and because of that, the interface region between the particle and the polymer is increasing considerably. So the idea is this, that if by incorporating a very small percentage, you can affect a large change, it cannot be due to the property of the filler as a whole. It must be something else, and it is understood that the property change happens because of the large increase in interfacial area with decrease in size of the particle and decrease in the interparticle distances. So this assumes that there is something happening at the interfaces, so that when the interfaces tend to take over the entire composite, the property of the composite changes, and the rule of mixtures that we are usually used to in case of micro composites hold no longer. To investigate this aspect, what we did was we took samples. As you can see here, we took a sample and we used the ICB electrode to create a surface discharge on the surface of the electrodes. And after several hours of degradation, we continue to measure, we continue to take laser profilometry. With laser profilometry, we scanned the surface, the degraded surface, and we were able to measure the amount of volume of the material that had been scooped out from the surface. Now, for example, if you look at these two pictures, you can clearly see, even with the naked eye, that more material has been scooped up from the top surface, which is the epoxy surface, rather than the nanofilled epoxy at the bottom. So if you are able to measure the volume of epoxy, volume of the surface that has been scooped up due to degradation on the surface, as you can see, neat epoxy, it increases with time of degradation. And the alumina platelets, which is only one nanometric dimension, these are micrometric sized fillers, but thickness is nanometric, we see that the volume decreases. The volume decreases even further when we have nanoparticles, that is the entire, it's a spherical nanoparticle, it's a nanometric sized particle. And if we look at the FSM images, we can see that the surface is considerably degraded for the epoxy, less degraded for the platelet, and even less degraded when you have a nanoparticle. So basically, we understand that if you have nanoparticles in a material, the material will be able to resist surface degradation. Why should this happen? So we put forward a hypothesis. Let us imagine that the particles are sitting and the particles are resistant to degradation. So when the discharge reaches the material, if it is neat epoxy, it scoops out large chunks of the material. When it is a filled material, the filled material on the top represents, in the bottom represents a microfilled material, and on the top, a schematic representation of a nanofilled material. So what happens is, let us assume that the particles are able to resist the degradation, they're not knocked off, and only the epoxy in the interparticle region is scooped out. The same phenomenon, let us assume, happens in microcomposites as well as nanocomposites. Now, because the interparticle distance in the nanocomposite is much lower, there are lesser amount of epoxy which can be scooped out from between the surfaces, whereas large chunks can be scooped out from the interparticle distances in the microcomposite. This might explain the kind of surface degradation that we see in the nanocomposites. Now, if this were true, it would mean that with time, with the passage of time, there would be more and more nanoparticles accumulating on the surface. So with degradation, what we should see is, we should see more and more alumina. In case of alumina, we should see more aluminium on the surface. So an ADX analysis shows exactly that as you have more and more degradation, the percentage of aluminium in case of alumina composites increases. If you use titanium nanocomposite in epoxy, titanium fillers, the content of titanium increases on the surface. So this kind of lends credence to our hypothesis. We also performed atomic force microscopy. And what we saw is that as surface degradation continued to happen on the surfaces, the topmost figure is an epoxy sample. And as you see, these are just chunks being removed. We don't see any structures here. But when you use a nanocomposite, you see spherical globules emerging. And with passage of time, so B is after maybe 6 hours, this is after 18 hours, this is after 24 hours. So with the passage of time, more and more such globules appear on the surface, and they are spherical. So it does seem that it is the spherical particles which are appearing on the surface. But there is a conundrum. The size of the globules that we see in AFM are much larger than the size of the particles, which means that it is not only the particles which are able to resist degradation, but also there must be some epoxy around the particle, which is sticking to the particle, which is also being able to resist degradation to a certain extent. So this is the first kind of inkling we had, that there is an interfacial region around the particles. So not only are the particles resistant to degradation, there is a region around the particles which contains epoxy which has been modified in some form. So there is the formation of an interface at the interface, which has properties different from the filler as well as the bulk polymer, and this interfacial region is being able to withstand degradation. So this is, now if we extrapolate this understanding to electrical treeing, what we see is that if you see treeing in neat epoxy, and then here you have alumina filled epoxy, and then you have silica filled epoxy, what we see is the tree is not able to progress as fast towards the other electrode as in neat epoxy. So putting in nanoparticles in the epoxy prevents tree propagation. Not only that, the tree channels are much finer. One thing is they tend not to progress in the axial direction, but the other thing that we see is they're much finer. In fact, they're very difficult to photograph. And of course, it is not possible to go into the tree channels and see what is happening. But if we expose the same samples to surface degradation, we see a repeat of what we had seen in our previous work. We see that In case of the nanocomposite, there is much less degradation, and the degradation seems to take place around certain spherical globules, and these globules have sizes much larger than the nanoparticles themselves. Now, again, we put forward a hypothesis that something very similar to the first surface degradation case must be happening inside the channels. So when you have, and let's say you have a tree tubule, a partial discharge takes place within the tree tubule. As a result, the tree walls get degraded, get eroded, and the tree channel widens. Now, our hypothesis is that if you have treeing in nanocomposites, there are also particles. This is, of course, a schematic representation. We're unlikely to have so many particles on the walls. You have particles sitting on the walls, and when the partial discharge happens, the walls are not degraded as much as they would be in the neat epoxy. The particles resist degradation, so there is not that amount of widening. The widening does not happen, and you have a situation where you have very filamentary channels and you have very small magnitude partial discharges. This we have seen that when you have treeing in nanocomposites, this is accompanied by low magnitude partial discharges, and you have smaller filamentary channels. Again, this is a hypothesis. What is the proof for that? We have an indirect proof. Now, when we take epoxy, what we see is that we can, if we visualize this under fluorescence microscopes, we see that there are fluorescent byproducts being formed in the tree channels. This precedes the formation of G and D channels. This is the Raman spectra. From the Raman spectra taken at various positions of the tree, we can see that there is the formation of the graphitic and disordered bands in certain regions of the trees. And if you make a comparison of the Raman spectra in case of epoxy and in case of the nanocomposites, what you can see is that it takes a much longer time for the G and D bands to appear, and it is much lesser. So basically, it really means that just as we have seen in the previous case, the particles are sitting on the walls of the surface of the walls of the tree channels, and the partial discharge cannot reach the epoxy, so that chemical decomposition or erosion can take place, and therefore carbonization of the channel is decayed. So in these two cases, this is the work by Munmoon Bardori, and the previous work was done by Parimal Maiti. So what we see is that definitely we see an indication that there is an interface around the nanoparticles, and this interface appears to be playing a pivotal role in deciding the composite characteristics. So let us look at what are the various interface models that are available in the literature. Now, the first model that I should talk about is, of course, Lewis model. Lewis proposed that if you have a filler, let's say the filler is phase A, and you have the bulk material, which is phase B, there would be an interfacial region between phase A and phase B, which would have properties over which the property would change as we go away from A to B. So over the distance of the interface, gradually the property changes. This is one aspect. The second aspect that he proposed is that the particle would have charge accumulation on the surface. That could be by reaction with the polymer. It could be due to absorption of charge from the bulk polymer. So let's say you have a surface charge on the filler. As a result, a counter charge would be formed in the interface, on the interface around the particle of opposite polarity. And so this is the Stern layer. So this two constitutes the electric double layer. And so this electric double layer has the effect of shielding the particle from Coulombic forces. And beyond the electric double layer, you would additionally have a diffuse layer over which charges of both polarity would be distributed. So as a whole, this entire layer is neutral, but this would impact the local field in the vicinity of the particle. The second model that we have is the Sagaropoulos model. In this, the idea is that around every particle, you have polymer chains which are very tightly, the interactions between the polymer chains and the surface of the nanoparticles causes the chains to not be able to, the mobility is affected. This is the first layer, which is seen by the black region surrounding the particles in the picture. And if you can see, there is a grayer region around the particles, which is the second layer. And in the second layer, the polymer chains retain more of their mobility. And when you have all these particles at a higher filler percentage, the particles may come together such that the second layer forms a unit, a kind of come together, and the mobility restrictions in the second layer become severe enough to compete with the first layer. And this indicated that he found there were 2 glass transition temperatures for a particular filled polymer. So this is one model. Then we have the more popular Tanaka's model, which is a multi-core model. Here he says that around the particle, there are 3 layers. In the first layer, the polymer is very tightly bound. In the second layer, it is not that tightly bound, but even then the polymer chain is restricted. Whereas in the third layer, they are comparatively freer to move around. So basically, the first layer may be around 1 nanometer, the second layer may be 10 nanometer, third layer may be 30, 50 nanometers. And over and above that, superimposed on all these 3 layers, there would be the electric double layer, as was proposed by Lewis. So this we have. Then we have the water shell model, which was given by Zhao Fothergill, where we have that the idea that around a nanoparticles absorb a lot of moisture. So around a nanoparticle, you would have a very thin layer of very tightly bound water particles, which will not contribute to charge mobility, charge carrier movement. Then you have a second layer where the water molecules are somewhat loosely bound, and when you have very low temperatures and low humidity, the second layer will also not contribute to charge movement. And there is the third layer, which has free water molecules. So this was the water shell model. Then we have the interface volume model, which was proposed by Raitzke-Kindersberger. The idea is that if you consider that each particle is uniform sphere, and if you assume that around each sphere, there is a region of uniform thickness, which constitutes the interfacial layer, then at a particular filler concentration, you would have maximum interface region. So as you increase the interfacial, as you increase the filler concentration, the interfacial volume also increases, and ultimately there will come a situation where these interfaces will overlap and they will not, the interfacial volume will not increase further. So there should be, for a particular thickness, there is a particular filler concentration at which you will see maximum interfacial volume. Why is this important? It is important because at this maximum interfacial, when you have the maximum interface volume, the deviation of the composite properties will be most from the neat material. So this is the idea. Of course, we still don't really know how exactly the interface behaves, but as I showed you, there are certain very hypotheses. There is a lot of work going on around the world, and some of the computational methodologies which have been used in my laboratory. Now, if you look at the computational methods that have been used by various research groups, you can broadly divide them into 2 classes. One is the indirect method and the other is the direct method. Most people have used indirect method, where we have indirect experimental measurements, and from the indirect, in the sense that we are not actually measuring any interface properties, we are measuring the composite properties, and from the composite properties, we are trying to estimate, find what we can about the interface. I will show that they tend to be somewhat inadequate. And the third method that I shall talk about is one of the direct methods. So let me go to these computational methodologies. The first methodology that I'm going to talk about is estimation of the interface properties from the interface volume model. This work was done by J.C. Pandey. So as I said, following the Retzke-Kindesberger model, what you can see is now what's the difference here is that we have not assumed any uniform dispersion or any particular size. We have actually taken FSM images of the real samples that we have worked with, and assuming that they are periodic, we have converted them into bitmap images. And from there, we have assumed interfaces of various thicknesses and tried to compute the interface volume. As you can see, as the interface thickness changes, the interfacial volume increases in different manners for different filler concentrations. So for example, this is for your 0.5 filler concentration. This is how it changes with thickness. We don't know what the thickness is, but if we assume a thickness, these are the plots show you how the interfacial volume changes as the thickness changes. Now we perform certain categorization experiments. When we looked at the breakdown strength, we see that when you incorporate alumina into epoxy, the breakdown strength increases up to 1%, at which point it does volte-face, and at 2 volume% it goes down. A similar trend was seen when we did space charge measurements with pulsed electroacoustic transducers. You have now nanocomposites reduce charge density. So the charge density is minimum at 1%, and then it again shoots up at 2%. Similarly, if you look at permittivity, the dielectric constant is highest at 1 volume% and again goes down at 2 volume%. Now, of course, there is an issue of dispersion here. I'll come to that later. But we more or less made sure from FSM images and a quantitative method that we use in the laboratory that 1%, 2%, 0.5%, all these samples had more or less similar dispersion. So we cannot attribute this change in the trend to dispersion. So something must be happening. And if we assume that this is because at 1% you have the maximum interfacial region, then if you look at this, this is only possible if you have a interfacial thickness of 200 nanometers and higher, because only at 200, so if you see 1 volume% does not have the maximum interfacial volume unless we assume a interface thickness of 200 nanometers and higher, when that is the highest curve. So that is the estimate that we have. But we are also aware that this estimate will change with many factors. For example, first and foremost is the uniformity of dispersion. So here I have a computational exercise where I have taken 3 different kinds of dispersion for the same volume%. This is uniformly distributed, of course, it's a computer experiment. This is weakly non-uniform, and this is very highly non-uniform. And as you can see, the interfacial volume that we estimate depends largely on the uniformity of dispersion. Apart from that, when we are using alumina particles of whatever, we are unlikely to have uniformly sized particles. So the particle size distribution also has to be considered. Periodicity of the sample cross-section across the entire sample has to be considered. So these issues are there. We are using a particular small computer sample for computation, but we are matching with results over a macroscopic composite sample. So that those issues are there. The next that I want to talk about, the next methodology is that one that uses dielectric spectroscopy. Here what we do is we use finite element analysis, of course, to have a representative volume element, a periodic volume. And we apply an electric field across the sample, and assuming periodicity, we try to compute the effective permittivity of the composite. Here also we have used FEM bitmap images of the real sample. And in each case, we take the particle positions, and around each particle position, we assume an interfacial thickness. We change the thickness, and we try to match the dielectric spectroscopy data obtained from lab measurements. And in this case, when we matched by varying the interfacial thickness to 3 times the diameter to 5 times the diameter of the particle, for a diameter of 40 nanometers for alumina and 1% volume fraction, we obtained an interfacial thickness of about 200 nanometers. And we also found a permittivity estimate over the entire range. We repeated the same experiment with, that was done by Rumana Zafar. We repeated the same experiment with barium titanate samples. In this case, the difference is that we were able to take the, we were able to measure the frequency, broadband frequency permittivity of the barium titanate nanopowder. And the estimates that we obtained for real permittivity and the interface thickness, we were able to obtain a match with experimental data for 1%, 2%, 5%, and 10% with the same data, which kind of gave some confidence in our results. But the thing is that we are still landing up with an interface thickness of 200 nanometer, which is much larger than expected. So this is the imaginary relative permittivity with frequency. So we are matching with imaginary permittivity, we are matching with real permittivity. And if you remember, in case of the interface volume thickness also, we are getting a value of 200 nanometer. But here we have changed the particle. So we're getting the same 200 nanometer for alumina, for barium titanate, which is kind of concerning in the sense that we are not really able to control the issues of dispersion to a very large extent. There is the issue of particle size distribution, and we have no confidence that we are able to get a unique match over a large frequency range. So my feeling at the end of this was that we seem to be getting very average values. Probably they are significant in some way, in a sense that there is an effective 200 nanometer region around the particles, which if we assume has an interfacial property different from the property of the filler and the particle, can account for or can predict the composite properties, the change in the composite properties. But it was very clear that at this point that we need to go deeper and we need to use direct measurements. So that is what we did. Electrostatic force microscopy. Now, what is electrostatic force microscopy? What it does is, as we scan the surface just in the manner of AFM, we get phase images over and above the topographical image. And these phase images are proportional. I mean, they give us the phase shift of the cantilever, and the phase shift in the cantilever occurs because of the change in electrostatic forces between the surface and the cantilever. Now, that means if we are over the filler or if you're over the polymer, because of the material change in material permittivity, the electrostatic force will change, and as a result, we would see it as in the phase image. So that is what we did. We did actual electrostatic EFM measurements, and we also built a finite element based computational model for the same. So here first we do the AFM of the sample. We zero in one of the particles. We scan with the EFM. We scan from the polymer across the surface of the particle till we reach the other ends of the polymer, and we do the same, we simulate the same surface and the same particle as we measure from the AFM surface topology in the computational finite elements model, where we compute the phase shift image. So we have an experimental phase shift image, we have a computational phase shift image, and we get to match them. How do we match them? We match them by assuming various thicknesses and various permittivities of the interfacial region across a single particle. So here we are being able to get rid of the averaging phenomena when we take a large number of particles. We are not concerned with dispersion. We are not concerned with particle size distribution. We are concentrating on a single particle, and then we repeat with various particles. And by matching the experimental data with the computational data for the EFM phase image, we were able to obtain a permittivity, an interface permittivity of 30, which we are only talking about real dielectric, real permittivity here, and a thickness between 15 to 25 nanometers, where we get a reasonable match. Now, to validate this, one more thing was done. What we did was we took the nanoparticles in the powder form and the nanoparticles in the composite, and we did a TEM analysis and an EFM analysis of both. Now, when you're doing a TEM analysis of the particle in the nanopowder form, nothing changes. The particle distribution or the mean particle diameter remains the same, whether it is computed from transmission TEM or whether it is computed from EFM, because the particles are loose. But in the nanocomposite form, we see that the mean particle diameter, which is obtained from the TEM, is 94 nanometers, but the mean particle diameter, which is obtained from EFM, is 137 nanometer. Now, what could be the reason for that? The reason for that is EFM measures a phase change. So EFM is able to sense a phase change over a larger diameter, and this can only happen if there is a phase change, not only at the junction of at the interface of the bulk polymer with the filler, but also around an interfacial region around the nanoparticle. So that means the EFM, the difference between the EFM diameter and the TEM diameter would give me an estimate of the thickness of the interface around the particle, because the EFM is giving me the phase difference across the particle as well as the interface. And calculated from this, we get an estimate of 22 nanometers, which reasonably matches our estimate that we obtained from direct EFM, matches a phase image of 50 to 30 nanometer. So with some confidence, we are able to say that we have a interfacial region of 15 to 30 nanometers, something like 22 nanometers, which has an interface dielectric constant of 30. 30 is kind of unreasonable, whereas 15 to 30 is acceptable. 30 seems to be a very much higher. We have to remember that this is not a real actual measure of the permittivity, but it is an effective permittivity of the interface. The permittivity in the interfacial region may not be constant. It may be changing gradually, etc., etc. And there is also the possibility that there is some charge present on the surface. So we did some further computations, and the same experimental and computational phase EFM data we were able to match if we assumed that over the interfacial region around the particle, there exists a volume charge distribution of negative charge. So it has to be negative charge, and if we assume a negative charge distribution of something like 2.8 into 10 to the power, I'm sorry, I don't remember the exact value, we are able to obtain a revised estimate of permittivity to be 8. Now, 8 is a much more acceptable dielectric constant of the modified interfacial polymer. So it is much more likely that you have morphological changes which modifies the permittivity of the interfacial region from 4 to 8, and on top of that you have also a charge on the interface. Let us remember that EFM only measures the electrostatic force, so it cannot distinguish between the effects due to charge and the effects due to permittivity. But of course, it is we still need to do a lot more of research to be able to come up with a consistent methodology. And we have to, it is quite evident that we have to use complementary techniques so that we can get a much better understanding and much better confidence in our estimates. So the quest for consistent methodology continues. We need to use better methods. One of the ways to go might be to use molecular dynamic simulations. Characterizing the interface is crucial to understanding and tailoring of the nanodielectric properties, and therefore we continue to work in this area. Thank you for listening, and that's all from me. Questions?
Thank you. If you have in the audience, if you have any questions, kindly write in the chat or unmute yourself and ask the question. We are not receiving any question. Next webinar will be on the 19th of December. The topic will be research for space charge. Research for space charge in solid insulating dielectrics, long history, current situation, and near future. Kindly join us on the 19th of December. And we have one question from Dr. Al-Tai. Good morning and evening. Can Dr. Gupta make the little, sorry, that was the question. Sorry. Okay, we have a question from from Satyamurthy. Dr. Gupta, can you please give me some details why scale parameter increases up to certain percentage, then it is decreasing? You are muted.
Yeah. Dr. Satyamurthy, are you talking about the scale parameter of the dielectric breakdown strength? Yeah, okay. So the scale parameter is an estimate of the central tendency to, it gives us an idea about how much the breakdown strength is increasing. Now, if you look at nanocomposites, if you look at the dielectric breakdown strength of nanocomposites, what we have seen is that when you incorporate fillers into a polymer, normally dielectric breakdown strength reduces considerably. So the same thing happens with nanofillers also. The breakdown strength does decrease. We are happy if the dielectric breakdown strength is not compromised to a great extent and we have improvement in other properties. So what we see is mostly, I would say that if you are seeing an increase in the scale parameters up to a certain percentage and then it is going down, the first thing that you need to check for is dispersion. That is the most common thing, because as your filler percentage increases, agglomeration becomes a greater possibility, and that is the most common thing that you will see. Now, if you are sure that agglomeration is not happening, then I would say that it is possible that at that filler percentage, the exact thing that I mentioned, the interfacial volume is maximum. So the best properties that you would get is likely to be at that filler percentage. And that you should verify by measuring other properties other than breakdown strength. I hope that answers your question.
Next, we have a question from Bobby. What filler properties tend to affect the conductivity of the composite?
I haven't done a lot of work on conductivity manipulation, but I would imagine that the surface properties, for example, I have seen that the humidity content, this I have seen results in various kinds of conductive processes like QDC and all. So it is possible that the surface manipulation is important rather than the filler. The surface manipulation may be important. The other thing is that you do not, I have talked about metal oxide fillers. These are all insulating fillers. If you use other kind of fillers like semiconducting fillers or conducting fillers, I think the conductivity is going to be impacted much more.
Okay. Next, we have a question from Albert. Did you find the space charge region appears to be negative or positive at the outermost region?
Yeah, we did not consider, we considered a uniform charge distribution across the entire interfacial region. And as far as I remember, it has to be negative to obtain a match with a,
Okay.
meaningful dielectric permittivity.
Okay. Next, we have a question from Gruber. Do you think charge accumulated on the filler material being present may be conditioned by applying external field and therefore diminished?
I don't exactly get the question, but what I would like to say is that when you have a filler material, the charge accumulation that I'm talking about is not necessarily at the interface between the filler and the material. The space charge accumulation happens throughout the thickness of the material. It is only in cases where you have conducting particles that you see interfacial charge accumulation around the surface of the particle, which can actually be seen. Of course, it might be there unless we go, I mean, for that we need techniques like EFM, AFM. We have not done that. But the PEM measures the charge across the thickness of the material, and that is happening throughout the material. So it happens only in the presence of applied external field. To hypothesize about what would happen to the interfacial charge at the surface of the particles, I am not sure, because those are very local things. I'm not sure how much they would be affected by the interface applied field. I'm not sure.
We have a next question from SoloWave. Dr. Gupta, how the nature of nanoparticles affect the surface degradation of polymer? For example, not only Al2O3 or silica, but maybe others.
Yeah, we have not done surface degradation with a lot of properties. We have done it with silica and alumina and silica, but then again, silica had less degradation than alumina, but then again, we didn't have the same sized particles. We could not obtain particles of the same material with different sizes. So silica showed less degradation, but we have to remember that the silica particles had a size which was half the size of the alumina particles. So yeah, I do not have any concrete evidence on that, but it should depend.
That's all for the questions till now. One more question from Satyamurthy. Can you please give me some detail about the Al2O3 nanofiller will act as a positive or negative charge while applying plus HVDC in breakdown test?
If I understand the question, you would like to know how the negative charge at the nanofiller surface will affect HVDC breakdown tests. I think it will affect, but maybe we can discuss this offline. This is something that we can explore. So please feel free to get in touch with me at ngupta@iitkac.in. Okay, yes. Yeah, please read out the question. Yeah.
From Manishi. Would you please share your comments on the role of surface modification on dielectric properties?
Yes, I have not covered that in this presentation. We have done a lot of studies on that, and yes, surface modification plays a very crucial role. For example, when we work with as received particles, the properties are quite different because there is a lot of water on the surface, and there is just van der Waals forces between the particles and the polymer. So the first thing we did was we heated the particles. When we heat the particles, the water is removed, but we have weak we just have very weak bonding. We don't have a strong bonding between the polymer and the particle, but yes, the water is removed. And then when you use a silent agent, and then again, what silent agent to use is another question. When you use a silent agent, we were able to achieve very strong covalent bonds between the particles and the polymer, and whatever property improvements we were getting were much better, and the particles, the composites, which much more had much more predictable behavior. You had more control over what to do. Yes, so surface modification is very important. Firstly, because of the bonding. Secondly, you need surface modification to have uniform dispersion, especially when we went up to 10% by volume of barium titanate particles. We spent a lot of time on surface modifications. Without that, it was impossible to have uniform dispersion. So yes, we have published something about that. Otherwise, please feel free to discuss offline.
Ma'am, please mention your email ID in the chat box so that people can reach you.
Thank you, Albert.
Okay, with this, I think we can end the webinar for today. And please join us on, okay, one more we got, okay. Thank you, Professor Nandini Gupta, for giving a good talk. And we will have a next webinar on 19th December. Please join us. Thank you very much.
Thank you, Ashok, and thanks to the YP team for having me here. It's been a pleasure.
Thank you.